Now we will see more in detail about how we design the finite state machine in Verilog. So we will see more complicated example. The shown example is electronic combination lock. So whenever we push the right sequence, the lock will be unlocked. So the combination target, so what we want is 0 1 0 1 1. If the key is pushed on that order, then the key will be unlocked. So we have a reset signal for here. So we will see how we make this the state diagram, and according to that state diagram we will write a Verilog module for that. Okay, basic building blocks. We can just briefly draw the lock, the internal. So we have a clock generator. We receive the clock from the clock generator, and we have input for button, for reset button and 0 button and 1 button, right? So first, as we know that we are having this asynchronous input for all these button signals, so we put synchronization block. Here we use the single synchronization flip-flop there, and finite state machine output will unlock, which will indicate the state of the lock. And also we also visualize what kind of state we are in. So for debugging purposes, we can generate the LED display output. The LED display output, we have lightning example, the combination. We have A, B, C, D, E, F, G light, depending on the how many output will be 1, 2, 3, 4, 5, 6, 7. So 7-bit output will turn on and off the LED elements, and we can visualize and make any some different number on the LED display. Okay, this is just basic big diagram of the finite state machine that we are going to implement. First step, we need to draw the state transition diagram. So from here, first we would prefer to design Moore machine, right? So Moore machine case, state define the output, right? So we make the as many states as possible as you want. So first reset state and key 0 state, and key 0 1 is state, and 0 1 1 0 1 0 and 0 1 0 1 and 0 1 0 1. So as we move from left to right and down and left, all the keys are properly entered. So, and then once that happens, so we will generate the unlock signal activated, and going back to reset state. Once we get the reset signals, we are getting the reset signal, right? We are if we are receiving 1, then we going back to reset signal. If we received 0, then we go to unlock. So this arrow, black arrow, indicate for the input condition will move the state transition, right? So for any reset state, in this reset state, if we receive the 0 key, then we go to 0. Next, if we receive the 1, we go to the next state, 0 1, and then receive the 0, then 0 1 0 and receive 1 0 1 0 1 and etc. like that. If we receive the wrong key, then sometime it going back to reset, and sometime it going back to the current state, right, to keep the sequence properly. So in any state, if you write the right sequence, it will keep continue. Make it transition to right state. Okay, so this is the final the state transition diagram. Once you determine the state transition diagram, writing that into Verilog will be straightforward. Let's write the Verilogs. First, module definition, log, and all the inputs and an output described. Input and outputs, right? Now, here is the key description. Starting, we need to specify state and next state variable. Remember, we have a flip-flop combination logic. It has feedback and the input. The input to the flip-flop would be next state. Output of the flip-flop will be state. Yeah? Right? The output will be determined. Final output will be determined only by the state. Right? State will go through the combination logic again to determine the output. So this is the big flow in your mind. So for the flip-flop, we need to define next state and state, right? We defining that in register type because we are gonna describe that into always statement. The always and sensitivity list, if you put the asterisk like this, any input condition, any input described inside the always statement will be included. This is a special keyword that you can use for if you have many inputs, it will be difficult to write all types of the input onto this sensitivity list. This is a simple, easier way to describe that all. So now inside this always statement, we have to describe the next state. Because this first always statement, we are describing this combination logic here, right? Now, next, once we define and describe this combination logic there, we have to describe the flip-flop. The flip-flop is easy, right? Whenever this clock rising edge happens, state will change to the current state, right? Next state generated from the combination logic, we receive that, and that we move that onto the flip-flop output, right? For the output combination logic, we describe using that assign statement. So any condition here, the output will be there. So for implementing combination logic, first and second, the first one we use the always statement. The second one we use the assign statement. For the output, it will be simpler logic, so we describe like using assign statement. But for the complicated combination logic description, we would prefer to use always statement. Okay, this is a kind of golden format you have to write for any finite state machine. You have to remember in your head. This is a very important template for your design. Okay, in between, so we are for the input, we can add the synchronization flip-flop, right, before we actually move that input into a combination logic. So synchronization we can also describe, okay, here. So let's design the synchronizer button. So whenever input comes in, rising edge happen, we change that to pulse, right? So we use the double synchronizer, and then we add some rising edge detector. So 1 0 detected, then it will pulse out. Okay, so this button, so describing this R1 and R2 flip-flop, we have a flip-flop definition here, R1 and an R2, feeding 1 and 2, R1, R2 goes there. For the R3, we also receive the R2 and it goes to R3, right? For this kind of non-blocking assignment, we first evaluate the right hand side, and then at the end we assign those values onto the left, right? So this is rising edge. So this action happen when the positive rising edge of the clock happen. Now, for describing this logic, we use assign statements. Since this is the wire, output is defined by wire by default. So you can add wire out, right? Or you can ignore that. By default, any variable we define on the input and output will be, by default, it will be defined as wire. Okay, so we describe that, the output. So this button module receives the clock and input and generate the pulse output, right? So this output will be received by the final state machine and do some process. Now we started with the parameter definition. Since we are having so many state and case, reset, 0 state, 0 1 state, like this. So we have 6 different states. We define variable with the state, define variable with some number, the binary number. So as reset stage, reset is encoded with 0, as 0 is encoded 1, etc. like this. So in Verilog, what we compare and process is the number, right? The binary number. So this is the string character. So we map that onto the number, right? So 1 is 0 0 0 1, 5 is 0 0, 5 is 0 1 0 1, right? 4 is 0 1 0 0, 3 is 0 0 1 1, and 2 is 0 0 1 0, like this. So since the maximum number of cases is 5, so the state can be decoded with only 3-bit, right? We can decode that, the state with the 3-bit. So that will be done by the CAD tool will optimize the number of bits to represent the state. Now let's describe inside the logic, how we determine the state. So in this case, we will define that if the reset signal is received, the next state will be as a reset. Otherwise, we will decode depending on the input button condition, right? If the input button is B0 is asserted, then we go to S0 state. Otherwise, we check again this. If the B1 button 1 is asserted, then we stay at S0. Otherwise, for no cases, we are assigning that the state means current state. So state doesn't change, right? Next state will be assigned to the state, right? So here you can, for your easier understand, so we can add some parentheses like this. But for Verilog, without having parentheses will be okay, because the condition, we check B0 first and then B1 first, B1 later, like that. So this is a natural order that for the tool to interpret. Okay, so we describe depending on the current state, we describe all the next state definition, right, according to the state transition diagram before. One thing to note is that we are defining default state. Why we define the default state? Because if we use a case statement, we only have how many? 6 different states, 6 states. But in binary, if we are represent this state in 3-bit binary, then the undefined number, undefined state exists, meaning without having the default state inside the combinational logic, you will have a latch, right? So such kind of thing will be disaster. We don't want to have that latch inside the combination logic. It will fail. So we must add some default state describing without instead hitting any state condition, right? We will go to jump to default. Okay, this is we already described that why we have to put this kind of a default state before, right? It's very important. So once we describe this always statement for the combination logic just before the flip-flop, right? This combination logic is described in this format, and then we describe that the always statement like this. Okay, for the positive edge, next state goes to state. So this is a state, and this input to the flip-flop is next state. Okay, this is very important. This is very golden template. We are following the template. When you design your circuit, we also follow this template. You must remember this kind of a description. Okay. Now we generate the output depending on the state. We will have an output. So if we reach to this 01011 state, then we will generate the output or circuit, right? How about debugging? For debugging purposes, output hex display is described by state variable and +1, so we have a 4-bit output. We use the concatenation, we curly bracket, right? This is output 4-bit defined. Hex display is 4-bit. We have a 1. State is 3-bit, right? 3-bit plus 1 bit, right? Total goes, well, it becomes 4-bit in total, right? This is the way we describe the number 1, B0 is 1 is number of bit. 2, B01, right? 2-bit 01 pattern, 2-bit 10 pattern, 2-bit 11 pattern, like this. In Verilog, we want to describe more clearly about the number of bits and the value, right? So this is the format that we use, right? Trying instead of describing that into like a 0, 1, 2, 3 like this, all these decimal numbers are actually not interpreted and not used. The machine actually take the binary number, so we prefer to write like 2-bit 00 and 2-bit 01 and 2-bit 10 and 2-bit 11 like that, right? So you try to describe that decimal into binary used in Verilog. Okay, this is the final Verilog implementation for the log. So we have input output definition, we define the wire, and we have a button. We use the button model here, button 0, button 1, and reset button. The button, so the definition of the button, we already showed that before, right? Look at that button module. If this follows the module definition, module of button, right? And define the parameter for the state, and we describe the state machine, and then flip-flop for the state, and what we have, and then assign and for the output, right? So assign for the hex display like this. Okay, this is final. I'm gonna ask you one question. For this kind of implementation, we use the flip-flop shown here. So for the reset, so reset it when the reset comes in, the combination logic receive that reset signal and assign that state, that to reset state. Is this be synchronous reset or asynchronous reset? For synchronous reset, the reset is happened on the next rising edge, right? For the asynchronous reset, the reset will be happen immediately whenever the reset signal comes in. What about this case? So if this is described like that, it is equivalent to some multiplexer is there, right? So 1 0. So if the reset comes in, so it is assigning reset like that, right? This kind of a combination logic will be a synchronous reset, right? This is synchronous reset implementation. If you want to have a asynchronous reset for the state, you have to describe that inside this always statement, right? So you refer that to the previous slides we had learned before, okay?